And what, they did another oxidation then?
Yeah. It doesn't matter which one we use, right? Came
That's right. So that would take us to here. Okay, and then they have to go through this last step. All right, so how should we do that?
You can just, that's they just did CH3OH and H plus.
Yeah, that's a very standard reaction. That's what you have a question about?
Yeah, you don't have to form the Cl first. It's so
No.
for this one.
Now there's a very standard name for this reaction. What do we call this?
Transesterification.
Not quite. Transesterification would be going.
Changing an ester with ester from another.
So this is just esterification. So esterification is definitely a very standard reaction that you're allowed to use here. This is just a normal esterification where we replace the OH with the OR. And the main reason why we don't need the SOCl2 is, again, we don't need to worry about that competing acid-base reaction here like we would if we added the ammonia. The main reason so the main reason we used the thionyl chloride in the previous case was because if we just add ammonia directly to the carboxylic acid, there's a competing acid-base reaction. But this is not nearly as basic as ammonia. This is not nearly as basic as ammonia. So this reaction, this is an equilibrium reaction, but if you start removing the products, you can pull it forward to get a good yield. So this is a pretty standard way to make an ester. I don't think it would be wrong to add the thionyl chloride, but maybe it's not quite as good because it would be more steps. So, okay.
Yeah.
Part D?
Yeah.
Okay. So it looks like they're definitely focusing on this oxidation reaction here. Here we have another synthesis. So it doesn't look like it's going to be hard to get the carboxyl group over here. Yeah. But we also have to add the bromines.
So block the para.
Then add bromines, then change it.
And because it's not what they did say, 2 equivalents of it.
So this is what they did next. So we added the sulfon group to block the para position. They said something weird here. They said that we can separate the para efficiently, but we can't separate the ortho efficiently. That seems kind of weird. It seems like if you can separate the para from the ortho, you should be able to separate the ortho from the para.
I mean,
but anyway,
if you separate the para from the ortho,
they are separated, right?
Yeah.
Well, I guess that's not necessarily so. Suppose that you have a situation where you have a bunch of paras and a bunch of orthos. Well, you could do a separation where some of the paras go here and some of the paras don't. And then the paras have been separated, but the orthos haven't been separated. So that's a possible thing here. Okay, so in any case, we were not allowed to just produce both ortho and para here because they did not say they had a good way to separate the ortho. So we have to block this position, and now we unblock it.
Does it matter if we unblock it first or carboxylate first?
Let's see, I don't see why it would make any difference. Although actually I guess it would be more efficient.
Wouldn't decarboxylate? Pardon? Wouldn't the carboxylic acid go through decarboxylation because we need to add heat to get rid of the SO3H?
That was a good question. So let's go through that. Actually, I think it would be good to do it second. So I would do.
They did it the other way around.
Oh, they did it first?
Because you have to add heat and water to get rid of the SO3H.
Oh, they said you needed heat for that?
Yeah.
Oh, well, it doesn't matter. So I think this way would work.
But now at this point, if you add heat and water.
Now this is, I think this is the way to do it. I forgot in the previous problems that we need aqueous acid to protonate this anyway. We need aqueous acid to protonate this anyway. Although I guess maybe we wouldn't need this if we were doing the sodium dichromate. But now we can add H3O plus and heat. And no, we don't need to worry about this decarboxylating.
Well, I think just they always put K-4OH with acid, and they used Na2Cr07. So if you would have done this step first, that would have had the OH.
That's true.
So,
All right, so I guess if you use the potassium permanganate, that's under basic conditions, and then you need an aqueous workup steps. And maybe the sodium dichromate is better because you can do that under acidic conditions.
yeah.
In any case,
It doesn't really matter which one,
Yeah.
as long as you're consistent.
yeah. Why can't this decarboxylate?
That one,
Yeah, this won't decarboxylate.
because it's so stable.
What are the conditions that we need for decarboxylation?
Oh, we need another carbonyl.
A beta carbonyl. Remember, you can only do the decarboxylation with a beta carbonyl carboxy group. So we don't have a beta carbonyl carboxy group here, so we don't need to worry about the decarboxylation.
And he would not affect that?
I don't think so. All right, so I think this would be fine, but it's always best to get into the habit of doing things like they do it in the book. So you said in the book first they took off the sulfone group and then they carboxylated this. Maybe there's some advantage to that. This seems to work fine to me, but if that's the way they did it in the book, maybe there's some advantage to that. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you.